it's a pity not to attend to this great event. Eurowings had some different plans than myself, so I was stuck into a strike, and now I will try to give you a presentation about the efficiency of electronic cleaning systems. I adopted my presentation a bit to current and today topics like the energy crisis we have, so I was more focused on the efficiency of our cleaning systems. I will start with a short introduction of the company and come back then to cliff notes, give you a few cliff notes of how we implement and how we consider ourselves to have the most efficient systems in the market. And I will finally close and bridge this today's presentation to the topic we have with the so-called cleaning grid, where I will show you how we think of the future of cleaning could and will look like. Now, we as Kolb, sitting here in Village, more than 30 years old, we have started as the pioneer in the cleaning of electronic tools and products. And since then, we have established a worldwide global network where we're using different distribution partners to serve our customers directly in their markets. On top of that, we have established our own entities as strategic hubs where we can have a bit more of presence in the certain and strategic regions. So now let's see if the technique will help us. I would like to show you a short image video of our company, just to give you a brief idea of how we consider ourselves and what our mission is. Is the sound? Is there any sound? No?
No.
Okay, that's bad. No, that's bad.
We can hear you, that's fine.
Yeah, okay. Yeah, many thanks for your attention on this stage. So as we have seen clearly in the video, for us, quality is not only determined as to meet the customer's expectations, but we always strive to extend that by far. And it was and it will be our future mission to have the most efficient systems in the industry. That's our philosophy, and that's also the mission we have. So in order to understand the needs of the customer, it's the one point on the one hand side. On the other hand side, you need to have the specific and proper product portfolio. And over the course of the year, we adopted ourselves by means of having a very flexible production. So we were able to provide always tailor-made solutions according to the customer's needs, and comprehensive on that to give the range of options and accessories. So now let's go into a bit more of detail. The cleaning process itself is determined by, or the cleaning result, better to say, is determined by 5 constitutive parameters. We have the machine, obviously. We need a certain detergent, what we can give a bit of chemical power to the system. You can add thermal energy or time, and or you can have intelligent software. So for ourselves, we determine, or we find out that the power of all criteria combined is much greater than the sum of its single dimensions. So that's why we had from the very beginning always not only the machinery and not only the appropriate chemistry, but we were always having our own software department developing and to utilize the machinery and the chemistry utmost. So with saying that, by doing that, we had the possibility to reduce temperature and time dramatically, and both will consequently end up in lower consumption of energy and in lower consumption of detergent. So that was always what we tried to do and what we will continue to do. Okay, let's come to the first dimension. The first dimension was here determined as the chemistry. I wanted to give you here a few points to understand how the traditional approaches were and how the modern approaches are now. So in former times, when the chemistry was not that available and not that developed, let's say, we were using a lot of salts. So the salts have a good cleaning result because it's highly aggressive, and it's even more aggressive the more temperature you give to the salt. So, and thus you can understand that having an old-fashioned detergent will always lead to mandatory use of elevated temperatures. That's one point. And the other point is, the higher the salt content is, the higher is the conductivity of the chemistry you're using, and the higher is the need of rinsing properly, just to reduce the conductivity level to the certain threshold, mostly requested by the customer or by other specifications. So the newer approach is to go with more chemistry and to have solvent water mixed chemistries. We call them the so-called half watery cleaners. And by doing that, we can utilize more of this chemical power in order to reduce a bit the ambient temperature, to reduce the temperature to the ambient temperature. This is one nice fact on that. Another thing is that these type of detergents are so-called buffer. So what does it mean? You're putting a lot of acid by your flux or whatever into the medium, and typically it gets very fast saturated. By buffering these agents, you are able to extend and to not have this dramatically drop to an acidic value. The next thing is we are always, by doing that, using these nanoparticles, we can have single phases homogeneous agents. This means that you will not have any separation by if you are not using the detergent, what happens typically with the old-fashioned ones. And with saying that, you can understand that if you want to have a well-mixed medium, you need to have an external mixing unit. This mixing unit again needs external drive and thus will consume more energy. And now I want to focus on the temperature. Everybody knows when we were in the past trying to clean our clothes at home, we typically use like 90 degrees or maybe 60 or whatsoever. And with the rise of new and modern formulations in the chemistry, we have been able to reduce at home our temperature, I don't know, 30 to 40 degrees. So, and that's the same approach what we will always strive to have with our machines. And the additional explanation why we are doing this, you will see here on the left-hand side. So what we see here is on the y-axis we have the vapor pressure, and on the x-axis we see the temperature. And what's pretty clearly to be seen is that it's not only that the vapor pressure rises with elevated temperatures as per expectation, but it rises exponentially. So, and to give you a short idea of the vapor pressure, the higher the vapor pressure is, the higher the gas ratio of the water is. So if you have, let's put it differently, the blue line, sorry, I need to use my mouse here. The blue line determines the thermodynamically balance between the gas phase and the liquid phase. So everything above that means you have gas, and below that it's liquid. So, and if you consider a temperature what we are typically operating in, 30 to 35 degrees, and what traditional old-fashioned detergents needed to have, like 70 degrees, it's not only the doubled pressure what you would have in the linear case, but it's 6 times higher. So, and this does mean you would increase your detergent consumption remarkably just by this vapor pressure. Okay, next slide. Another thing is what we did from the very beginning is we were always searching for the highest efficient components in order to have later on a machine working very efficient. So we decided very early to move from mechanically and sealed pumps to the so-called magnetic coupled pumps, where you do not have any interaction between the drive and the pump. So this results in low maintenance, no sealings, no maintenance, and sorry, and in lower energy needed to provide similar pressures. On the right-hand side, you see our rotor. This is the rotor, and what we're doing here is we have 2 asynchronous working rotors in the operation, and we're doing that to have a clear and thorough wetting all over the product, and thus you have a continuous flow over the product, and you can consequently reduce the time. Another thing is we have here nozzles where we use the kinetical power of the detergent streaming in here by this tube coming here, and then it's just rotating by the force of the detergent flow. So we don't need any external driving units to move our rotors. The next thing I would like to show you is our patented drying models we are using. We have the so-called BMH, and we have the CWA. The Venturi mixed hot air, that's what it stands for, is quite simple. You have a heater providing you an air stream with a temperature of about 600 degrees. And by means of using the Venturi tube, you just suck in from the atmosphere the cold air, and you have pretty fast temperature profile, what you need in the chamber fast. So it's very fast. That's the one thing. And depending on the product you want to dry, you need not only the convective energy to dry, but you also need the kinetic force of the air. And to realize that in our systems, we're using a side channel blower. What you will see here inside is a turbine. This turbine starts rotating, and in addition, just by compression of the air, you also heat the air up, so you have a good combination of a thermal and a kinetic drying process. We can also provide machines with both systems concurrently, and by doing that, we can almost produce our own weather in the chamber, so we are able to almost provide every temperature profile needed. And the next few slides, I would like to give you an idea on how we deal with the topic of scarcity of water. We always strive to reduce the water needed, what's necessarily needed in the process, as much as possible. And before explaining how we do it, I would like to give you an analogy to the Oktoberfest. If you were attending in former times, you would have seen that there was one cleaning basin and maybe one rinse basin. So then you were already good. So what they did, they used glasses, put it into the cleaning basin, and then just took the cross-contamination and put it back to the rinse basin. And by doing that, you will saturate your rinse basin pretty fast. And thus, as a consequence, you will need to change this basin more often to have clear glasses, right? So, and what they did then is they just added another basin. So to have one cleaning, one pre-rinse, and one final rinse. And just by doing that, by separating these processes, you have been able to either survive the full day without doing one water change. And this is what we did from the very beginning into our machines. Currently, we provide one tank system, two tanks, but I will focus on two tank and three tank system just to explain the idea behind. What we see here on the left-hand side is the circuit diagram of a representative machine of ourselves, and such machine would have about 100-liter water consumption per cycle. If you would go then to the three-tank system, so you would divide the rinse tank into two tanks, having one for the pre-rinse and one for the clear rinse, you would be able already to reduce your consumption remarkably to the half. And if you continue that, we have an external processing unit where we reprocess the water, going through heavy metal absorbers and through the eye cartridges. And by doing that, you can reduce it already to 5 liters per cycle. So thinking of an XH7 machine has a capacity of about 500 to 550 Eurocard PCBs. So I would say it's a pretty good value. This was not enough for ourselves, so we approached our R&D department and said, hey guys, what is if we could reduce it to almost zero? So they came up with the project Zero Discharge, and they provided us with the prototype. We did some testing, and we have been able to reduce the water consumption to lower than 2 liters. So, and how do we did that? I will try to explain you here. Typically, the similar approach what we had before, we divided one tank into two tanks, and so we thought, yeah, what will happen if you would just follow this logic further and try to divide the tank B, that's here a bit highlighted, into more parts. So, yeah, okay. As a short step back for increasing of the understanding. Typically, you have here you clean your boards. The boards, the detergent flows back into the tank. The tank is contaminated with the parts coming from the boards. So then you have a certain carryover. The rinse water is contaminated, and then again the carryover for the clear rinse. And what we did here is we divided the tank B, what you can use typically 15 times before you need to do a full water change. We divided it into 3 parts, and this is the interesting, we added a counter current stream, fresh water here. And this fresh water current does the following: it takes over a bit of the contamination from tank C, a bit from the tank B, and a bit from the tank, let's say from tank 3, 2, and 1, and brings it out to the dispose area. And by doing that, it's not necessary anymore to do any water change, because you keep the balance in the tanks equally, and you will not have, it will just follow up to a certain saturation, and that's it. And yeah, this was the great success what we had so far, and would like to promote that final prototype. There are a few adjustments we need to do. There are a few questions: what happens if water stays too long in the tank? I mean, everybody knows from the aquarium what happens. So there are a few things we will still need to investigate before we can promote it to the market. Yeah, now I'm at the end of my presentation. I would like to give you a further outlook of of what we are working on. We are working on a so-called cleaning grid, and there's a few ideas behind. The one is to have a possibility to implement inline into the lines of the production. This is the one idea. The other idea is you can use this, as you see here, with the 5 slide-in units. You can use it as a buffer to clean in times where the operator is not on site. And or you are increasing the capacity remarkably just by separating the loading and the unloading process from the process itself. And here again, I've brought you a short video to give you an idea how this will work at the end. So here's the end of the line. This is the unload on this side. The fresh cleans part coming out, going through the conveyor feeder to the unload area. The contaminated products go in, machine closed, starts process, and so on and so forth. And the second machine is doing the same thing. It's just every second slide-in unit goes into the one machine and every second in the other, subsequently following. Yeah, that was how we interpret machine efficiency and having an efficient process in the cleaning industry. And now I'm here to answer your questions.
Right, thank you, Christian.